In this video, I will explain a simple example of geometric deep learning and what it means and how we can learn it. We'll try to build a network that can classify digits on the rotated MNIST dataset. So here, for our experiment, I will rotate the usual MNIST dataset pictures by a random rotation. I will load this data into a standard dataset and a rotated dataset. So notice we have a normal dataset with no rotation and a rotated test dataset, and we'll train the model using the normal dataset. Okay, so we build a simple CNN. Here our CNN is composed of convolutional ReLU, maxpool, and linear layer, and the classification head for the MNIST digits. We will write some script for training and evaluation. We will use Adam optimizer and cross entropy loss. And you can see the training and the evaluation functions in the notebook. We will train this simple model for 3 epoch. Notice we have an accuracy on the normal MNIST test dataset and accuracy on the rotated MNIST. We can see after 1 epoch our accuracy on the normal dataset is 98% and almost 40% for the rotated MNIST. So how we can solve this problem? Basically, we have to build a new kind of neural network that respects the symmetry of the data, which is called an equivariant convolutional neural network. So in this package, you can check the GitHub. These layers, these convolutional layers is implemented, and we are going to use this to complete our experiment. So this package include other layers. You see like steerable CNNs, which is another concept related to the geometry of the CNN. Here we just need to build an equivariant CNN that respects some symmetry. So an equivariant neural network guarantees a specific transformation behavior of the feature space under transformation of their input. So it means that the feature space has to remain the same if we apply some transformation to our input. Okay, so to implement these layers, it requires some knowledge from group theory and representation theory and harmonic analysis, which I have created video and posted on the channel if you are interested to learn the theoretical basis. Here we are just looking at the code and this repo. So you can see what we mean by an equivariant neural network. So we have an input image like here, which is rotating, and we can see that we have a feature field or an stabilized view. Okay, so despite the rotation, the feature space has to remain the same. Below you can see the experimental results of this model also. So we have to decide our network, the new model that we are building, respect which symmetries it is like SO2, which is a group, and or SO3, which is another group. As you see that we have a good result based on the symmetry of the network. Okay, so there is two notebooks for an introductory exposure to this material. Here I will show you these notebooks, and I will create more videos, and I will post it explaining this concept. So basically we need knowledge from group theory, representation theory, as I told you. And we have to relate these concepts to the machine learning, to our feature space, and to the input data. So these notebooks tries to cover some of these concepts from the mathematics and implementation. And the second notebook tries to build an equivariant CNN. So this CNN model, we just use the pre-coded layers that exist already, and we have to define a symmetry group. This is like equivalent to 8 rotations. So if we rotate the MNIST dataset like by 360 divided by 8 degrees, the network will have a knowledge of this symmetry, so it doesn't matter if we rotate this network that much. So you can see the code and the implementation here, some of it, and the result of the testing in their notebooks. So I suggest that you have a look at this GitHub repo. Also, it does not include all the basics. I have another notebook here which I have added more details here, and we will go through it in the future videos, like how to define a group, for example, like a cyclic group of order 8, which we used in the previous notebook, how we can sample elements from it, and other concepts like what is a representation, what is a feature field, and how we can incorporate different layers like ReLU in this model with the equivariant convolutional neural network that we have. And I have run the same experiment in that notebooks, and you can see the result. We have like 93% accuracy. So subscribe and like the video so you can see more content about this.